Hello guys. Okay, we start homework. Okay, there were some questions. I wouldn't ask everything. I hope if you have questions also. But my question is, how about these? Remember these equal, more than, plus. Are they symmetries or operators or what are those? Remember this question?
That's the third question. Yeah.
Yeah, this is the question. Yeah.
I did. It's over there.
Yeah. Papa said that the question was to give an example of what operators are. Like
Yeah.
Like a book could be an operator because it changes how you think.
Okay.
Or like a bus because it gets you from one place to another.
Okay, guys. Examples are for you, okay? You may discuss with Papa, okay? My question is, what about this? Remember this, the third question. That's equal, more, less, plus, minus, multiply. What are those things? What do you think?
Operations.
Oh.
They are operations.
Operators, okay. Are they symmetries too?
Symmetry.
Are they symmetries? What do you think? Yes, you think yes. So if they are symmetries, they should conserve something. Remember, symmetry means that something is preserved, right? Something is not changed.
Well,
okay?
an equal sign does that.
Equals, yeah, very easy, right? E equals B, so it's the same, right? Nothing changed, right? That's easy, that's correct. What about this? Like A greater than B, what is preserved here? What is preserved here in this thing?
That's not true.
A equals B.
It's
it's A greater than B.
Not equal, but
Well, in order to be able to compare them, they need to have something in common.
Right. That's a good idea. Do you understand, guys? What your papa is saying?
No. Oh wait, those could be like two whole numbers.
No, like for example, you cannot compare numbers and strings.
Yeah.
Oh, they're the same thing. They're the same thing.
Yeah, there should be something that should be comparable, right? So at least something is like, for example, maybe numbers. Then numbers are consist of ones, right? 1 plus 1, so some ones. Many ones here, right? And this is just more than that. That's okay. Or maybe not even numbers, maybe something else. I don't know what. But you may think about it. But it's great, comparable. What about plus? Okay, like A plus B. I think should they be comparable too or not? The first question.
They don't need to.
Huh? Yeah, of course. You cannot plus something different. A lion plus what? Plus sheep. They're not additive things. They should be comparable.
Yeah, you can't do flowers plus sheep.
And the same. Yeah. And the same.
You can do sheep plus wolf because they're both animals. If you want to talk animals.
Right. But then you talk about animals. So again, animals are comparable, right? When you talk about animals, it's a comparable thing. Animals on the left, animals on the right.
I think they are because you can't compare two different things.
Yeah. Okay, so the same, I think, with minus and multiplication, right? They're the same thing. Or what else? Maybe some general thing. What do you think? What is preserved like in this, except that they are comparable and equal in this case? Yes. What else? What do you think? What is still the same in this operation? A equals B. Take it as a whole. What is still there? What is preserved? What is preserved? Huh?
They're part of the equation.
Part of the A and B are part of the equation. Yes, that's correct. They're part of the equation. They're comparable, right? That's simple, close. But what else? Any clues? I will give a clue. They're the same here, and here, almost the same.
Operations?
Yeah, operations themselves. This thing, it's not a number, right? But it's a name of something, right? This is operation. This is operation. This is operation. And this operation, whatever A and B are in this is still the same. Whatever A and B here, this is still the same. And plus here, it's the same too. Also, I will give you another maybe form of operator, right? It's like this. Like if you say A plus B equals C, right?
Yeah.
We may say that this thing plus B equals is an operator, the whole thing. Take it as a whole word, right? And then we have on the left A and on the right C. So A transforms to C, and transforms means exactly that, plus B equals. That's how mathematics shows that this is still a language. You know, these are letters of the language, and this is a word. So this is a word which, in short, you can put an arrow, right? A transformed to C, but you mean this, right? So it's another form of operator. There are many forms. By the way, operators like plus, minus, multiplication, they are often called binary, because when you write A plus B equals C, right? You may change engine A and B, so the two variables can be changed. So they, like binary operator. Two, like a operator when you put two variables to get the result. Like here you get one variable and get B. Here one variable greater than B. Those are binary. These are called, I'm not sure that I pronounce it, unary or unary, right? Antosha.
That's a binary operator.
This again. If you may take it like this, if the result takes true, right? Like it's in coding. Usually they do that. Like binary operator when the result of it is true or false. But if it's when you put A here, the result is B here. So it is unary operated in this. But the pronunciation is unary.
Unary, yeah.
Unary. Okay. So well, let's finish. I will finish with the thing, and I will start the theme. Any questions, by the way, for the previous lecture?
No, but we still need to do the paradoxes.
Paradoxes. Okay. Paradoxes. We'll talk about paradoxes many times, so you'll think about it. So we'll talk about it anyway. So now we'll talk about that. Okay. Yes. Yes. Yes.
But you know what? You know what's funny? I came up with one, and I told Mama and Papa, and you know what I knew? And they told me it's actually the theory of relativity. Well, then you technically didn't come up with it then, right? He said that's not true. I did come up with it.
Tell the other what it is.
So so I came up with this myself, but it turned out it was the theory of relativity. So when I said, so you know when someone is walking forward, it's as if they're actually walking forward. But if someone is walking the opposite way, it's as if the person who's walking forward is actually walking backward.
Looking for and where is it exactly in the theory of relativity?
Walking towards each other.
When two people walking towards each other, it's like one person's, for you, you're going forward, but then for the other person, you're going backward. So are you going forward or backward?
I'm not sure what you're talking about. Maybe if you can maybe give me more details. Maybe is it there are two theories of relativity. Do you mean this curved space? This
it's not the theory of relativity. I don't know. Well, kind of. When two people walk towards each other, one is walking forward. You're walking towards someone. You're walking forward, but for the other person, you going backwards.
Oh yeah. Oh yeah, of course, yes. So yes, it's, okay, yeah. But it's not theory of relativity. It's just relativity principle, right?
Yeah.
Yes.
What it kind of was.
Yeah. It's actually it is a paradox if you think about it. Yes, it's very interesting thing. It's the paradox of oppositions. That's why they call opposing things. By the way, we have two objects, right? One is looking on this one, right? The other is looking this way, and for some reason they're looking opposite directions, right? Yeah. Maybe they are the same. Maybe it's even like if it's like a number one, like one here, like 1 equals 1. Remember, one looks at one this side, this one, the same one, right? Looks opposite. It is a paradox. It's the same one. It actually equals, even equals. It's still the same thing. So it's just a person may be looking to itself, right? Somehow. But it looks like looking into the mirror, right? So you're staying here, but your reflection is opposite to you, inversed, right? So yeah, there are lots of things. That's a good thing. Yeah. Okay. Good. Good. Very good. Okay. Now about vectors. Okay. And invariants. Invariants. I remember. I remind you. Invariants. It's something that is not changed. Whatever we do around, like it's very closely connected with the idea of science that actually the nature outside, it does not depend on us actually. You know, we can jump around, dance, you know, talk, but the nature is still the same. You know, mountains still erupt, you know, the volcanoes still erupt, sun goes up and down, you know, planets rotating around their stars and everything going on, and we live somehow, you know, in this environment, right? Environment changing by itself. So we talk about objects, the objective world, which does not depend on us. So invariance is about objects. So some of the objects we have, like the number, right? For example, number of the trees in the forest, right? Trees in the forest, like whatever, 100, 121, right? For example. When we come to the forest, like pretty often, there's not time to when the trees, really new trees goes up, right? But we come, the number does not change usually. So when we come, forest is not really changing, but it's changing still. Everything is changed with the time. But when you look for the certain time, it's not changing. That's why we call it objective. So not changing, not depending on us. At least it's not going without us. It does not really affect the growth of a forest. If you don't put a plant, manufacturing plant, like the really, you know, damaging environment, right, and which kill the forest, that's why a little comes from objective, a little far further from objective ideas. But anyway, yeah, I think you got what objective means. So, like for example, this is one object. Let's name it A. Some object, whatever it is. It can be you know, a number, can be somebody, can be a planet, whatever, universe, object A. And it is invariant, so it is an object, objective. Now we have another object, like it's very objective too, and it's here, somewhere, right? Now let's think about interesting thing. Okay, when we may change around, we may dance around, you know, we may change our view, we look from this side, from that side, from that side, you know, we can, you know, grow in size ourselves or maybe shrink ourselves, but still the objects are still the same. They're objective, they're objects. Now, imagine that we have some transformation. So the object A, under some process, something happens, and object A is transformed into object B.
This is a paradox.
Okay, maybe, yes, the paradoxes are everywhere, yes, I agree. But we enter a little different thing. So A is transformed into B, right? And maybe we are ourselves transformed it. Like we got some tools, you know, like maybe A is a whole vase and B is a broken vase, right? Both are objects, different objects. So we just put a hammer, you know, hit with the hammer object A, and it got broken into parts, you know, with object B. So this is our action, right? So we put our strength into it. So we transform into it. So it depends on us. The process depends on us. So if we don't take a hammer, nothing will happen, right? B maybe would not even exist, or whatever, may happen something else. So there are things, actually, you should understand that there are things that are not objective. Those things are called subjective. Subjective or subject which is connected with the subject or with us or somebody. Me, you, we're all subjects, right? For example, wolf may be subject too, if we take it as a, you know, some free being, you know, comes and do something like ate. Like for example, A is a rabbit, right? And wolf ate a rabbit, and now B, something, not rabbit. Okay. So those processes are subjective and they depend on us. But let's imagine something different, not subjective but objective process. So the process which happened with no our involvement. We do not, we're never involved in this, we're just looking at this, right? Something like maybe the tide in the ocean, like A is the ocean low tide, B is the ocean high tide, or whatever, right? Or maybe planet in one phase, another phase, like the moon. Moon is like growing, or moon is like, how it is called? Not growing. They need
Shrinking?
new moon, old moon, whatever. Different phases of moon, right? So something that does not depend on us. In this case, we call this process objective process. Objective process, right? Objective transformation. And this objective thing is by itself sort of an object. It's a little maybe dynamic because it's transformation, A transformed into B, but still it's an object. So whatever we do, whatever we dance around or talk or whatever do, if we do not touch A and B, the process will go like it did before. It still transforms A into B. And in this case, we call this object, we call this process vector. General vector. There are lots of vectors you will be meeting with these vectors in mathematics later, but this is a generalized vector. So vector is, they call vector is a ordered pair of objects, objects A and object B. Ordered means this arrow, A transformed into B and not back. A into B. A is first, B is second. So vector in general understanding, vector, it is an objective. So invariant, ordered, so ordered pair of objects. So this is like maybe the most general definition of a vector. So whatever we do, we still hear this picture, right? We still see this picture. So examples of vectors, like speed. We're riding the car.
Speed. That's velocity.
Yeah, velocity. Okay. Speed or velocity, right?
Well,
like,
speed is not a vector.
Okay, I'm sorry. I don't know what the speed means. That's okay. Velocity. Okay. Okay, 100 kilometers per hour. For example. So what it has? First, it has the not orientation, or how it is called.
Direction.
Direction, yes. First has direction, and then it has the so-called norm or value.
Size, yeah.
This 100 kilometers per hour. So it has a value, and then what are the vectors? Like if you. Yes, sure.
What's velocity?
It is just.
Velocity, it's actually, I think it's just a speed. Yeah, they'd say it's not a vector. I don't know what speed is.
Velocity is speed and direction.
Oh, speed times direction.
Oh, speed means the value, right?
Divided by?
So that's, yeah, okay, this is English thing. So 100, the number, it is speed, right? And direction means that it's not only speed, but it has some direction, orientation. From A to B, right? From point A, like from Boston to Toronto, but not back, but not back.
Yes.
And speed is 100 kilometers per hour, right? The other examples of vector is like this called radius vector, like a radius of a circle. Again, if you put it like this, right, to a certain point, this is the center of a circle, right? And here a certain point. So you have this, it's called radius vector, radius vector. Oh, without dash or with dash. So the other interesting example of vector which you should think about, really, it is the one thing that we spoke in logic, which is called, believe it or not, syllogism.
Syllogism?
Syllogism is the main thing in logic, right? And usually it sounds like this. Like for example, this classic syllogism is, you know, there was Socrates, right? Socrates, if I pronounce it correctly.
Socrates.
Sorry? Socrates?
Socrates.
Huh?
Oh, yeah.
Socrates.
Socrates.
Socrates, okay. He lived something like 400 years before Christ. The greatest, one of the greatest philosophers in history. And the classic syllogism is about him. I would say like this. Socrates, so Socrates, is human. Right? Then, this is true, right? This phrase logically is true.
Socrates is human, yeah.
Human.
It says Socrates.
Human is
human.
Human is mortal. So we have two.
Mortal.
Mortal. So she dies sometime. Any human. Now, so we say this thing. Socrates is, so it's some sort of operator. Socrates is human, and human is mortal. So we have two things. They looks like vectors. They're oriented and they're pair, right? SHHM, right? And in logic, if those things are both true, this vector is true too. It's true also.
Yeah.
So we say that Socrates is mortal.
Makes sense? Makes sense.
So this is true. Because is this true and this true, this is true. So you see, we see something interesting, right? We have not only these looks like vectors, right?
Looks like a triangle.
Yeah, it's like a triangle, yeah. And this is actually called a rule of triangle. For a rule of triangle.
What?
For vectors. This rule allows you to, when you know that something is a vector, so it's invariant and it has a oriented pair. If it's like this, when we talk about this a little, just if it's like this, then this triangle, this rule of triangle works okay, and you have the thing that we call addition of a vector or sum of two vectors. So vectors SH plus vector HM equals SM.
Wait.
Socrates human plus human is mortal equals Socrates mortal.
Yeah.
And this is algebraic form of syllogism.
That's like.
And this is true for any vector, if it is vector. So when we look at this, and look like Socrates is a human, it's a sort of an object, right? So pretty independent on many others. Like humans are an object. Mortal is a feature, objective feature. Something can be mortal or not. So it looks like objective, and this is one of the examples of generalized vectors.
No, that's not true. No, that is almost never true.
If you go back, like if you, for example, if you try to inverse, right? Invert the vector, not sh, but hs, right? So you come into something else. Because Socrates is human, yes, this is correct. But human is Socrates, if you go back, right? It will be probably false.
It's false because we are not Socrates. Yeah.
Yes, exactly. The same thing like for mortal. Not each mortal is human, right? Not each mortal is human. Right? Some mortals like dogs are mortal, but they're not humans. So when you go back, goes something else.
That's pretty interesting, actually.
Yeah.
Didn't expect that.
Yep. So think about this, because some questions I have to use some questions with this.
Does not mean B implies A.
Now we come to this rule of triangle, which is used very often in summarizing, editing vectors everywhere. And one of the first thing is that if you have vector A to B, right, and you try to do that, AB plus BA, what will be the result? What do you think? A transforms to B.
To AB.
And B transforms to?
It's to AB.
No, A, the first thing is A transformed into B, right?
Uh-huh.
We go this way. Now, plus means that we continue. Remember triangle? We should continue from here with the vector, with that vector. But this vector is totally opposite to this. It's BA. So it goes like this.
So what do you get? If you travel from Toronto to Boston and from Boston to Toronto,
Yeah.
how far from where you started?
How far at all?
How far? What's the number?
0. Oh, so that would be equal AB.
Is AB 0? Distance from Toronto to
No,
Boston?
equal 0, 0.
We may write it AA, right?
Is it AA?
Well, why not? AA.
Which
Or,
is 0, right?
but remember, sometimes it is already a vector, right? You write it as a vector, pair, right? AB is a pair, BA is a pair. Sometimes they write like this to show that this is vector. Sometimes they denote like this. So AA is to a vector, but it has null, so 0 length, right? AA. You're still in the same place, right? And actually, maybe it is a vector, but does it have a direction like AA? What do you think?
No.
No.
Yeah, but these things are just standing in
So
one
it's
spot.
maybe it's a vector, but it's a very weird vector. So with the null, so it's called null vector, by the way. Null vector, yeah. Sometimes, but it's a very interesting. It's not the same thing like 0 is very weird number. It is a number, but it's lots of weird things. A very paradoxical number. The same thing, this null vector is very paradoxical. You may write it 0 and may write like the sign of vector over 0, right? To understand. So it's something like this, but still, it's 0. Okay. The other thing for the vectors, you can try to do that, like AB plus AB. What would it be? What do you think?
AB plus AB. I think it still means AA. No, no. To be.
To be.
To be.
Okay. You may think of this. Okay, the 0 question. Okay, question number 0. You may think on this. What is actually what is this? Okay,
But
AB.
do your vectors have a fixed starting point? Do they?
No, but no. That's a good question. Actually, that's a good question. Yeah. In these cases that we talked before, right? They all have certain positions. Like vector AB starts with A and then goes to B, right? Vector BA it starts with B and goes further, right? But this vector starts from A, right? So it's not easy to understand how to make this addition. Addition usually means that addition means what this, that you have vector this, and then you start from this, and then start from this, 1 plus, you see? You start from the point, the next point, the next point, the next point. Here it starts from the same point. It's not totally totally correct to write it like this. So when people thought about this long enough, they come to the idea of, I'm not sure about the terms, about free vectors. So the vector can be moved, because remember, vector is an invariant thing, right? It is like an object. It does not, like an object, it is not actually really connected with this, with the beginning and the end. And they said that the vector can be moved to any other places. So you can take vector AB, you may write it like this to define it like a separate object, like A. Do not use these points, the beginning and the end, right? And then, if you want to add it to itself, for example, you move this vector here, like this, so it have the same direction, the same length. Remember? The length, the value, same value, length, and same direction. And in this case, if you do that, it looks like 2A, right?
Yeah.
They are summarized. It's the use of triangle. Exactly. This is triangle. You see? 1 to here, here to here, and then this is the resulting vector. It's like a little degenerated triangle, but it's still triangle. And it is defined as 2A. So A plus A, it's 2A. And of course, this way, if you go this way, you may do many times, like maybe n times A, right? So you may add vectors and of course subtract, the same thing, and do other interesting things. So vector look, they talk about like certainly free things. You can move them, but in parallel way. This vector A has the same direction and length is not changed. Something like this. So in the beginning of idea, the vector was attached or hooked to the points, starting point and end point, but at the end point and starting points are actually changing. They look like variables actually there. So the vector is a form of it's an operator actually. So it's like function, like function change one to another, one number to another. Here vector change one object into another object, and the object can be taken as variable objects. So you can submit. You can put any object into this place, and it will be result in some other object in this place. But the process itself will be the same. It's like the same meal, you know, just you put different type of grain into it. You know, you can get different type of flour out, right? But the process is still the same. Okay, now a little. Okay. Remember we were talking about system of coordinates like number x's, right? Like x, y, right? So if you have some point somewhere here, like this is point 0, right? And this is maybe point A. So you can put a vector that's connect point A with point 0 with point A. Like for example, it's one of the examples of vectors, which usually that is what when they say vector, usually people mean exactly this. The vector is something with some coordinate axis, x and y, and something like this. What we can say about this vector, right? They usually define so-called basis vectors. Basis vectors are vectors that have value or length
away from your face
equals 1. So just 1, and which are directed to the direction of the number x's, 1, 2, x, y, and others. So it is like this, 1. This is called basis vector, and this vector usually is denoted like ex. X is index. It means that this is vector with the direction along axis x. And here we have, of course, E with the index y, right?
Huh?
Now if you have this vector, how you can define it through these basis vectors? Those axes are called frame of reference. It's a very important definition. Frame of reference are just certain things, like here are number x's, x and y, which allow us to measure vectors, points and coordinates of all these things. But usually, like in real life, it's not just lines, right, with some numbers on them. Usually there are some devices, some measuring devices, like rulers, for example, right, that we use. We put one rule, another time, and we measure the distance. So how we do it here? We do it like this. It's called projection.
Oh yeah, we've done this.
Yeah, this is orthogonal. It's called orthogonal projection. Orthogonal. It means that the angle here is the right angle. So we put, we draw the line with the right angle here, and we measure this distance, right? With the units 1. Like for example, here is like maybe 3 axis. For example, there may be different, maybe 3.5. It's interesting, but maybe 3.5 or maybe less. The same thing we do with y. We put orthogonal projection here, right? And we see how many are here. Maybe 4, for example. And if you look here and recall the rule of triangles, right? So you see one vector here and another vector here. See, one and another one. And this is exactly the same as this. It's the same direction, right? And the same value.
Oh yeah.
Right? Because this is a parallelogram. Not parallelogram.
It's very similar, yeah, to a lot of things that we've done. Yeah.
Yeah, it may be proved, but it's in here pretty easily, right? So in this case, you may say that this vector, like OA, it is a sum of two vectors. Like first is 3EX plus this, which is 4EY. And it's called, I think, expansion, or how it is called? Expansion into base vectors? I'm not sure about the terms.
I think it's a reduction to the base, yeah.
Reduction, I think not reduction. Anyway, expansion, reduction, but anyway, you see it as a sum of basis vectors with certain numbers. These numbers, 3 and 4, are called coordinates of vector OA. Coordinates. And do you see that they're the same as coordinates of point A actually here? So we have vector is defined, the vector is defined by two numbers, 3 and 4, which are called coordinates. And this you may do with any vector, like vector OB, for example. Again, do this, right? Measure and make a sum and have another coordinates. It's I think it's easy. You understand, right?
Yeah, it's cool.
Yeah, it's cool. Now, you may imagine that the same thing you can do in 3D. This is X. Oh, sorry, not. This is Y, right? This is X. And this is Z. Which all of these are right angles. They say also that X is orthogonal, so I have a right angle with the plane ZY. Y is orthogonal to the plane ZX, and Z is orthogonal to the plane YX. So they're all like planes, right? Like the corner of the room, right? The corner of the room. This is the corner, and there are there are two walls and this is the floor, right? So this is 3D picture. If you have 3D picture, and again you have some point, but now it's not in not on the plane, not on the 2D, but 3D, right? You can put a vector or a here, right? And interesting enough, you can do the same thing because you can do projection first to the plane, like this one, and this will be like projection of this vector to the plane, this one, and again you put projection with the right angle to these things. And then you can first define, like for example, this vector. You can put it a. How you call this thing a strip?
Prime.
A prime, right? So this point belongs to the plane xz, right? So this vector or a, this a prime, right? It stays on the plane. So this vector you can put as sum of this vector and this vector, right? Which you know this is something. You may say some number like x, this is number like z, right? And this, again, it's orthogonal projection to the plane. All these angles are right, so just like this. And this vector, again, you may write it here, like this. This is like y, index y, this. And then you have for this vector OA again three coordinates x, y, and z. So x, y, and z. Usually they denote it like a little differently. So this they usually write like x. Like x with index x, like this y, maybe not x because too many x's, right? Like a, then b, e, y, and c, again z, e, z. A little too maybe I shouldn't write it, but anyway, you may understand this. Three things, like three coordinates, like x, b, y, and c, z. So you have three basis vectors, ex, ey, and ez, and three coordinates for the vector, ax, by, and cz. Okay, so just one small thing before we coming to the finish. You may think, and people actually not only thought but actually used it very heavily in the 20th century, from the beginning of the 20th century and the whole century up to now. They thought about space with many dimensions, not 3D, but for example ND, right, where n is any number, ND dimension. So many other axes here, all of them are with the right angle with all the arrows, like lot n of axes, and of course n of basis vectors. And actually not only like this, but they move further, and one of the very talented, some call him geniuses, mathematicians of the beginning of the 20th century, David Hilbert. If I'm always mixing, I think it's Hilbert, yeah. David Hilbert come to the idea of space with the infinite number of dimensions.
That's pretty cool.
So, like this, right?
Wait, how did you draw something like that?
Interesting enough, it's It is possible. And example is this. One of the examples of the, like how we draw vector, right? In infinite number of dimensions, right? For example, I will give you an example. Remember we put the plots of functions like x squared, right? Remember? It's like this, right? So you have infinite number of x's, of variable x, here, right? And actually, what they say that each number here, it is an index. Remember there were basis vectors. Remember? Like ex, right? So this is the index, and they say that each number here, it is at this index. So there is E1, E2, E3, right? And to the infinity. Okay? And even not only that, but even those like E1.5, E1.7, I don't know, whatever, E0.1. Okay, so not only integer numbers, but also, how they called, real numbers, all the real numbers, actually. So there's continuum, this is infinity, continuum number of indexes. So lots and lots and lots of basis vectors. So here are indexes of basis vectors, right? And what are the coordinates of these basis vectors? Here are they. How you point them? Here are they.
Well, it could be
like values, the value. So each vector has this value. So all these vectors which we see on this plot, okay, they represent actually the infinite, the vector in the infinite number of dimensions. So the function, any function like this, or general y equals any function of x, this is the general notation of function, equals f of x. F is this process or operator, you may say. So this actually is a vector in infinite dimensional space. And there are also lots of mathematics around it, like lots and lots and lots and lots. So, okay, we probably should be finishing. So just example that you may understand that this goes a little further than just 3 dimensions or 4 dimensions, you know, or even many dimensions. It's like infinite number of dimensions, and not only infinite, but continuum of these dimensions. Okay, questions to this?
No, you answered every single question, did like always.
Okay, what question?
What? No. I said you answered.
Get close and talk.
You answer every single question always, so.
Okay, so I have questions for you. Okay, guys.
I know.
Okay, the first question is, find your own examples of syllogisms and vectors involved. Some just
What?
your own examples of syllogisms.
Examples of syllogisms. Okay.
The second is think about it. What can be a frame of reference? If you know what the frame of reference is in mathematics, right? Like a number of x's, like axis numbers, right? And dimensions and everything, right? So what can be a frame of reference in logic? You see, remember the logic looks like vectors too, right? And they have a row of triangle. So what can you imagine can be a frame of reference in logic? And the third question is connected with something, I'm sorry to say one word about this. Oh, you'll write the question, okay, and then I'll see. Find examples. The third question is find examples of reference frame changes and invariants of this transformation. Okay, so frame of reference. What is change in the general? Just I would say, what is the general called by change of frame of reference? Frame of reference, like for example, on the plane is two number x's, right? X and y, right? Now, for example, the first is called shift. Shift means that you just moved both of these x's to a certain place. Like for example, you move it like here. So this is x prime and y prime, right? This is the beginning of the first frame of reference, and this is the beginning O prime, the beginning of the other. So we just moved it. All the x's are parallel. X is parallel, x prime is parallel x, I prime is parallel to y. So this is called shift. So just moving, right? This is one change of reference. Of course, if you see some point here, like point A, right? The point is not changed anywhere, but the coordinates will be changed, right? Coordinates in this frame of reference are different from coordinates in this frame of reference. So just think about it, right? Another, maybe like this. You have x and y, and then you rotate it to a certain angle around point 0. Rotate. So this axis goes like here, I prime, y prime, and this goes like here, x prime. So this is angle alpha. This is the same angle, so because they still should be with the right angle, both of this. So the whole thing just rotated this way or that way. This is called rotation. Rotation. So again, if you have point A or the vector, they are both invariant, both are objects, not changed whatever we do. We change the frame of reference, so the coordinates of the point are different, coordinates of the vector are different, but the frame of reference is different. And the other thing is called scale transformation, which means that you just maybe you took different scale, right? So for example, you have this basis vector here, right? This would be ex, right? And here is ey, right? And then you change the scale, so you just make the size bigger. You pull x and y to these directions, right? So the basis vectors become, like for example, here ex prime and here ey prime. So the size, the map become a different scale, but you should understand that the point is still here. Point is not changing because it's an object. It's not changing because what we do, whatever. We just used another mapping. So this is scale change or scaling. Probably scaling, right? So this is about frame of reference, and the question is the third, what I told you, that find examples of reference frames. Maybe some other what you can find. Okay. Okay, guys.
I don't understand the third question.
Okay, the third question. Again, maybe you can write it. Find examples of reference frame changes and invariants of these transformations. Transformations are frame changes.
All right. So examples of reference frame changes. So these are the examples that you gave us.
No, I gave you 3, but there are many of them. They're they're infinite amount. So just give your own examples and think about them.
Sure, but hold on. So you gave us an example of scale shift rotation. You want us to give more examples of reference frame changes.
Yeah.
But you said something about invariance. What does that mean?
Oh no, I told that. I said. Remember, A is object invariant, right? Everywhere it's invariant. Vectors, like this vector, OA, is invariant. Here vector, OA is invariant. Here is invariant.
So other than you want other invariants other than vector and a point?
Maybe not, but you just whatever you can imagine, right? So just think about it. Yes, maybe some others. Maybe you can invent some others. Why not? There are lots of them. Trust me. There are like infinite number of both, and invariants and transformations. But first of all, think about other transformation. Shift, rotation, scaling are the simplest ones, right? They are everywhere. Just imagine your own. That's the question. And the same with each thing comes certain invariants. Maybe not like this. Okay, I would say that in some transformation, some invariants which are invariant here, here, and here, maybe not invariant in your transformation that you suggest.
Okay.
It may be partly subjective. Remember that if you're wrong, you do something on your own, and it's somehow connected with the object. The object turns to be not object anymore. It becomes dependent on you. It would not be objective. And to understand this is exactly what you should do. There are objective things and subjective things. By the way, I would say that like the main fundamental theories of today, there are theory of relativity and quantum mechanics, right? They are the basis of physics from the beginning of the 20th century and until now. They are the basis fundamentals of all physics. It's experimentally proven thousands and thousands of times. They're very good, and both are not totally objective, because unfortunately, whatever we do, like in our world, like we try to measure something, right? In like, for example, in the planets, astronomy, whatever. If we try to measure, we use some devices, right? They're real devices. We cannot measure something with nothing, right? We should have some devices to measure it, right? To measure anything. But devices has, for example, they has a mass. They have weight, and weight gravitates. And when you put some measuring device into something, it starts pulling the other objects to you. So you not only measuring, but you're doing something else. You are involving, like you are trying to measure the movement of the planets, but you put like a big satellite there. Satellite pulls the planets, and the planet orbits are changed already. And this comes to very serious problem in a certain way. In quantum mechanics, it's even much worse. There are small particles which are totally interact with each other, and when you're trying to measure something there, you're using your device. But experimental device, it consists of these particles. It consists of quanta, and quanta are all interacting each other all the time, like billions and billions of times. So it's very difficult to get us from involvement on the objects. Objects are not that object anymore, unfortunately. So just to you to understand. Okay. Any questions?
No, that's it.
Okay, guys. Then. Okay. Okay.
Okay. Спасибо большое.
Nice to talk to you.